this video, we are going to look at how we can manage and leverage GPU slices, mixed slices in a Kubernetes cluster. Before I describe the demo in more details, let me briefly start the cluster. So the cluster will have 2 nodes, and I'm starting the cluster. So in this demo, we are going to look at 3 possible mechanisms to manage GPUs slices on the cluster. The first one is going to use the NVIDIA GPU operator. The second one is going to use, instead of the operator, dynamic resource allocation, as we discussed. And the third one is going to complement the array with the InstaSlice admission controller. So as my cluster is starting, here's on the right, top right of my screen, the kind of workloads I'm going to try to run on this cluster. It consists of 2 pods. Both of them are running, simple CUDA kernels. And they are going to request different mix slices, different sizes of mix slices. The large pod is going to request a 2G 10GB slice, whereas the small pod is going to request 1G 5GB slice. And for the sake of it, I'm going to request 2, even if the demo doesn't really require it. So here you can see that the cluster has been created. It has 2 nodes, and one of these nodes has one A100 GPUs, and one of these nodes has 2 A100 GPUs, so that we can demonstrate a multi-node, multi-GPU per node cluster. So in order to use the GPU operator, I'm going to first start it, right, and then explain. So what I've done here is to start with is configure the GPU operator by labeling my nodes in this way to say I like all my GPUs to be sliced in equals partitions of type with profile 1G 5GB. And then I'm starting the GPU operator, and really the important piece of configuration here is I've set this parameter here, which says, although at this point in time, in the initial phase of the demo, all my slices are going to be homogeneous. I eventually want to switch to heterogeneous slices with different sizes, and therefore I'm telling the operator, please understand that I'm going to use, again, an heterogeneous set of slices. So let's look at the state of the operator. So the operator is starting. It's actually taking quite a while, in particular because really the operator starts twice in this configuration, because it starts first ignoring the configuration I specify, and then realize I've asked my GPUs to be prepared in a certain way, and so it's going to implement that. So it's still initializing, and hopefully within a second or 2 it will complete. Within a minute or 2 it will complete. Almost there. So it's only the validator that doesn't run, so we can move on. So now what you can see in my cluster is indeed the GPU operator has configured my GPUs, and now under every GPU I see I have 7 1G 5GB slides available. Moreover, if I look at the list of allocatable resources in the cluster, this is reflected by the scheduler, where I can see on one node I have 7 slices available, and another node I have 14 slices available. So now I can run my tests workloads, and creating the 2 pods, and what will happen, of course, with these test workloads is the small pod that requests slices of types available in the cluster is going to easily run, whereas the second one is going to be forever blocked in pending state. So you can see also, by the way, when I look at the logs of the pods, that the pod has been properly configured to have access to exactly 2 slices of the GPU. The rest, it hasn't requested, is not accessible from the GPU, and my current kernel ran properly. And if I look at the logs of the status of my large pod, I can see that the scheduler is reporting that I don't have the slices I need available. So let me get rid of these pods and point out that with the GPU operator, I can actually reconfigure the slice of that GPUs. It's just a matter of relabeling. So in that case, I'm going to say, please reconfigure the GPU so that I have, rather than homogeneous slices, I have a more of a balanced configuration with different types of slices. Again, this is a costly operation that takes a minute or 2 to be processed. So let's wait for this to happen, and then we'll look again at the state of our GPUs and our available resources in the cluster. And the point is, with this configuration, I should now have enough of the 1G 5GB slices and of the 2G 10GB slices to run these workloads, to run the two pods in these workloads concurrently. So the GPU operator has observed the change in configuration and is actually doing the job of reconfiguring the system. So this is happening. We're almost there. It's just the validation also that hasn't run, so we're going to ignore that and take a look at the GPUs. So now if I look at my GPUs, you can see they've been reconfigured in an homogeneous, well, the 3 GPUs have been reconfigured in the same way, showing 2 1G 5GB partition per GPU, 1 2G 10GB, and 1 3G 20GB. And if I look at the allocatable resource on my cluster, this is reflected because now, for instance, the node with 1 GPU is reflecting the corresponding number of slices. I can deploy my workload again, and if I now look at my pods, I will see that my 2 pods have completed. If I look at the large pod, I will see not get logs, just logs. I will see that it's actually running with a different partition size as expected. Okay, so that concludes the demo about the GPU operator. Let me stop this cluster, restart from scratch, this time to use the array. So as I'm going through the process of starting the DRay demo, let me point out that in order to run this DRay demo, because DRay is an alpha feature, I have to configure the cluster appropriately, and this is what I've been doing here with this configuration, which is pretty verbose, but at the high level, the 2 important considerations are: first, I'm specifying Kubernetes version 1.27, which is the one that the DRay driver from NVIDIA I'm using is, meant to run against. And second, I've enabled the configuration flags to actually be able to use the array on the cluster. So once the cluster is, the previous cluster terminates, I'll be able to create a new cluster and start from there. While this is ongoing, let me show you again the workload. So as you know, we started with workloads using resource limits that specifies specified as follows, right? Which is what we need for the GPU cluster. But in order to use the array, as we discussed, we're going to have a different configuration, right? So for instance, if I take a look at the small pods, rather than having resource limits here, I'm going to have resource so let me start the cluster in the meantime. I'm going to have resource claims, right? 1 per slice I want. So in the case of the small pods, where I had 2 of the 1G 5GB slices, I need to express 2 claims, and I need to, create those claims, and then I need to bind those claims to my container. I need to do the same thing for the large pod. And moreover, I will need all the metadata, all the configuration of those parameters and claims that is required by the DRay infrastructure at the Kubernetes level, and also the NVIDIA DRay driver to, again, precisely configure what my claims are, right? So it's, as we discussed before, a bit involved. So now I created my cluster. I'm just going to install DRay on my cluster. This is actually much faster than installing the GPU operator. Fortunately, let's run through that, and let's have a look at the GPUs once this is done. So I created my cluster, I deployed the array. Now what's interesting about the array is nothing has happened with my GPUs. They're still unconfigured, if you want. They're MIG enabled, but they have no partitions. And now I can go in and deploy my workload, this time expressed with claims, and I can take a look at my pods and my resource claims. I can see the pods are pending, and the claims are already in the process of being allocated, and now my containers are running, I'm almost there, and they're both completed, right? So if I look at the logs of the small pods, it's exactly the same as before, which is great. Moreover, if I look at the GPUs, I can now see that I had partitions, slices created of my GPUs on demand to satisfy these two workloads. Now I can delete all the pods, and I can try to go back and run the workloads expressed in this, traditional, much simpler way. If I do this, I'm going to get stuck, obviously, because there's no such resource available in the cluster. If I look, for instance, at the status of the pod, this thing is telling me that I don't have this kind of resource in the cluster because, again, DRA doesn't function in terms of extended resources, but DRA requires claims. So that's where we enter the last piece of the demo, which is to add InstaSlice, or the InstaSlice admission controller, to this picture. So I'm going to install the InstaSlice admission controller. I'm going to wait for a second because it takes maybe 15 seconds for the pod admission controller to get online, and then I'm going to try to deploy this workload again. And my pods are created now. And now what happens is this is actually going to work, right? And the reason is what InstaSlice has been doing under the hood is taking the workload as specified here and essentially rewrite it to the workload as specified there. So if I look again at the logs of my pods, it's what I expect. If I also look at the pods, get pod small minus o YAML, I can see that although I submitted the pod in this manner, if I look at the content, the definition of the pod, it has been implicitly rewritten by InstaSlice in terms of claims, claim templates, and so on. This concludes the demo and shows you again that with the GPU operator, we can slice GPUs, we can in fact even dynamically reconfigure GPUs, but only entire GPUs. Whereas with DRA, we can actually slice GPUs on demand when the workloads actually make requests for specific configurations. And moreover, using the InstaSlice admission controller, I can continue to use the GPUs, use resource limits with DRA exactly as I was doing with the GPU operator. Thank you for listening.